if we look at the percent ionization of weak acids, this was actually going to be a metric that tells us to what degree our acid is ionized. We know that strong acids are 100% ionized in solution. But we can calculate the percent ionization of weak acids as well. In doing so, the percent ionization would be equal to the amount or the concentration of ionized HA, whatever that happens to be, whatever our weak acid is, over the amount or concentration of total HA. And so we can kind of approximate this. The amount that's ionized at equilibrium would be equal to our H+. Because we know that, say, for a generic acid, goes to H+ and A-, for every molecule of HA that dissociates, we get one H+ out. So, we have our ice table. We have some value of HA. We know that we're going to subtract X and add X. So whatever these numbers happen to be. We know that therefore X is going to be equal to the amount of ionized acid. So it's just stoichiometry, right? We know we're going to produce some amount of H+ for every HA molecule that dissociates. So we can actually kind of rearrange this equation. One more important thing is that this is the equilibrium value. So the kind of complete amount at equilibrium. And so if we want to rearrange this equation, percent ionization is going to be your concentration of H+ at equilibrium and the total amount of HA. Since this is just looking at the ionized amount, the total amount is actually the amount we started with. So that'll be HA initially. So percent since this is a percent, we'll multiply by 100, of course. We're looking at the difference of the H+ at equilibrium over the total initial concentration of HA. As I've written it here, that would be just X over Y minus X. I'm sorry, X over Y, because it should be initial. And if we go ahead, we can plug in the numbers from our last problem, and we can figure out what the percent ionization is. Although we already did it, but we'll find out. So, oh, by the way, if you do use Wolfram alpha to figure out X for that last problem, you'll get 0.00149 instead of the 0.0015 that we got using our assumption. So, as you see, your answer is very, very slightly different, negligibly so. So, you can save yourself some time by using that assumption. So, with this, we saw that the H+ value is 0.0015, and our initial concentration is 0.0125. And so the percent ionization is going to be equal to our 0.0015 molar over 0.125 molar times 100%. And in fact, we already did this calculation when we were evaluating whether our approximation was acceptable. So you can approximate when the percent ionization is 5 or below. And we saw for this one that we got 1.2%. So in 100 or 0.125 molar acetic acid, only 1% of molecules break apart on average, right? They're, of course, continuously forming and breaking apart again, but we see that the percent ionization for this concentration of acetic acid is 1.2%. And so we can establish this. So just another metric we have. Alrighty. Hope you enjoyed that. So now you know weak acids don't dissociate completely. Acetic acid only dissociates 1.2%.